last time we were looking at linked decision tables, and what I told you was to look at the table and try to interpret it. Now, I will do it slightly differently. I will give the set of rules, and from that I will go to the linked decision tables to explain how the linking is being done. Now, the table corresponds to a particular word statement or a set of rules given by a government office, some mythical government office, does not exist in reality. Okay. So, the promotion rules are as follows. This particular service has 6 salary points. What is meant by salary points is that at a given salary point you get a certain amount of salary. When you advance to the next salary point, you get some increment, extra salary, and there are a number of different salary points, and each salary point one gets promoted from one to the other based on certain conditions to be fulfilled by the candidate who is up for promotion. Okay. Provided the candidate's conduct, diligence and efficiency are considered satisfactory. That means these 3 are conditions which are essential to satisfy. That means all 3 of them have got to satisfy. If any one of them is failed, then I think the rules will not apply. Okay. And he has spent 1 year as class 1 officer and has satisfactorily passed the departmental test. He advances to the next salary point. If it is he is in point 1 or point 2, that means what it says is that there are, at the beginning it says there are 6 salary points. For salary point 1 and 2, 1 or 2, there are, that is a rule. And if he is in a higher salary point, that is 3 or above, then if his conduct, diligence and efficiency are considered satisfactory, and if 1 year has elapsed since his last increment and he has satisfactorily completed the departmental test, the departmental course, then he advances to the next higher salary point. The first one talks about test to be passed as when he is in salary 1 or point 1 or 2. In this case, it is a course to be completed, then only advance to the next salary, higher salary point. It is obvious that there are only 6 salary points. So, once you reach the 6th salary point, you kind of saturate. There is no further promotion possibility, because there is no such thing as 7th salary point. So, the first thing we do is to look at the number of conditions in this set of rules. The conditions are conduct, diligence, efficiency, salary point, whether he is spent 1 year as a class 1 officer, whether he has passed a departmental test, and whether his salary point is above 2, and also whether he has undergone a departmental course, completed departmental course. So, the total number of conditions, if you count all of them, becomes as shown in this table: 4 in the first, plus 2 6, plus 3 7. Total of 7 conditions are there. If you put all the 7 conditions in one table, the table will become extremely unwieldy. That is the reason why we break up, because 7 conditions means there are possible 2 to the 7 rules, and 2 to the 7 rules means there is 128 different rules, and that is extremely difficult to one after the other consider and so on. So, it is much better to kind of break up the problem into smaller parts, so that each part is somewhat self-contained, and that part is linked to the next set of decisions to be taken. So, the first is the way I have broken it up. The breaking up is not there is no unique way of breaking up. I have particularly used a particular way of breaking up, which I consider a logical method of breaking up. you may consider something else, but you can try it out. But my feeling is that this is reasonably all right in terms of the way in which I have done it. So, if the conduct, diligence and efficiency, all three are important. So, I put all of them in the same table, and we know that if all of them are satisfied, then only you have to go into the rest of the promotion rules or going to the next salary point and so on. If none of them is actually, any one of them is not satisfied, then you do not have to really examine further which salary point he is in and things like that in terms of the rest of the rules. Now, similarly, when a person is in salary point 6, okay, and if the answer is yes to that, then there is it means that if he is not in salary point 6, then only all these things apply. If he is in salary point 6, then that is the highest salary point. Beyond that, there is no promotion possibility. So, we look at the fact that if he is in a salary point which is 6 or below, that it is not 6, but that means it is below 6, because there are only 6 possibilities, okay, 1, 2, 3, 4, 5. I could have put salary point less than or equal to 6, okay, but it is all right. I mean, in fact, it may be more appropriate to put less than or equal to 6. No, that means it is 6 or above. Okay. If it is 6 above, has no meaning. That is the reason I put equal, because there is nothing called 7th salary point. Okay. So, if the answer to the first question is no, and all the others are satisfied, that is his conduct, diligence and efficiency are all okay, then you proceed further to check various other conditions to decide whether to advance him to the next salary point or not. Otherwise, you say no promotion, because if he is in salary point 6 already, then obviously there is no promotion. If any of the conduct, diligence or efficiency is not okay, obviously he is not going to be promoted. Okay. So, now I put a cross against go to table 2. What it means is that you have to examine table 2 now if the first rule is satisfied. So, now you go to salary the table number 2. There I will look at all cases where the salary point is greater than 2, because there is a particular rule for 1 and 2 and there is another rule for greater than 2. So, I am taking salary point greater than 2. No, that means it is either 1 or 2. Okay. So, if it is either 1 or 2, or 1 year as a class 1 officer, he has finished 1 year as a class 1 officer and he has passed the departmental test, then advance to the next salary point. That is what the rule says. So, if the salary point is not greater than 2, that means it is either 1 or 2, and he has not finished 1 year as a class 1 officer, then there is no promotion. Similarly, if he has not passed the departmental test, then also there is no promotion. If the salary point is greater than 2, that means if it is 3, 4 or 5, then you go to table number 3, which is the next set of rules. If you go to table 3, that means beyond salary point 2, you have to complete a departmental course. So, decision table 3 says because the last one, that salary point is greater than 2, you go to the table 3. Okay. In other case, the first rule obviously says you automatically go to the next salary point, because you have satisfied the condition specified by that rule. Then the next salary point, once you go there, you have to find out whether departmental course has been attended. He has successfully attended the departmental course, and 1 year has been completed since the last increment. In other words, you do not advance anybody to the next salary point as per the rules if not even 1 year is over since he got the last promotion. So, he has completed 1 year since the last increment and completed with the course, then you can take him to the next salary point, else there is no promotion. So, observe that one can branch between tables, and whenever a complex rules are given, it is a good idea or a good practice to break it up into a set of manageable parts. So, in fact, the advantage of this is that this also can be followed very easily by the manager who gave you a set of rules. Then when you look at these rules, he can kind of convert that, like I tried to do last time, back to a word statement and see if it actually is what he intended as the rules, or there is some error and he may like to change the policy and so on. Okay. So, the whole idea is to be able to also be a very good communication aid to the user, apart from the person who is going to take this table and do further work on it, which will be primarily to interpret it and write a equivalent computer program for it and so on. And that is exactly the idea of breaking up. I would now like to start looking at a very important part of the decision table terminology, namely at the end of developing a decision table, you would like to find out whether the table is correct, that means there is no logical errors in it, and you would like to also find out that it is complete, that means no rules are left out, and you also would like to find out if there are redundant rules, that is rules which are not necessary, which can be eliminated. So, the rest of these lectures I am going to be devoting, in fact rest of this lecture particularly, I will be devoting to defining certain terms to find out the logical correctness of decision table. The point is that a lot of this is not really referred to in most textbooks, and I have done a fair amount of work in this, and it is really based on a lot of work done by me and my students in terms of trying to find out how to exactly determine the correctness of tables, because one of the greatest advantages of a tabular structure is to some extent, if there are small tables, by inspection determine the correctness or incorrectness, and also reduce any extra rules which are there, or if any contradictions are there and so on and so forth. Okay. And if it is a very large problem with a lot of linked decision tables, in fact we can even write a computer program to automate this testing process. In other words, the methodology I am going to say is amenable to writing as an algorithm and later on converting the algorithm to a computer program. That means, in other words, some of the aspects of this which are syntactic to some extent and not entirely semantic can be automatically checked, and there are certain cases where even the semantics can be checked by a program. I will kind of indicate those types of tables, because not every table is amenable to that kind of a checking. I am going to essentially tell you later on what types of tables are amenable to automated checking by a computer program. Another advantage of a table is that you can generate test data easily, because if you are able to generate data which will satisfy all the rules one after the other, then if you test these data then when you test using this test data, the actions are taken by the program can be compared against the actions which are specified in the original specification, and if they are the same, then you say that the test has passed, otherwise you say the test has failed. So, generating the test data is easy because it is based on the values which are assigned to the conditions which are there in the table. Now, we will look at this condition, this table. This table has got two conditions. C1 is x greater than 60 and C2 is x less than 40, and the rules say that if C1 there is x is greater than 60, then do action A1, and if x is less than 40, do action A2. That is what it says, and it puts dashes to indicate that in case number 1, rule number 1, you do not have to test condition C2, and rule number 2, you do not have to test condition C1. So, now this is exactly what the sometimes when people interpret rules into tables, they put a dash against irrelevant condition testing, which I have done in the last in fact in the last table I put a lot of dashes, because in the second rule the departmental test whether he is passed or failed is irrelevant, because he is going to get no promotion, because he has not completed 1 year as class 1 officer. So, the dash is put somewhat from the word statement automatically by the person who develops it. So, sometimes the dashes which you put can be misleading, and so that is the reason why we would like to be able to expand out and see whether the dashes hide some information which is intended. So, in this case, for instance, I will expand the dashes into yes and no. So, the first rule will expand into R11 and R12, that means yes and yes no, and similarly R2 will expand into R21 and R22, where C1 is now the dash is expanded into no and yes. So, you can now see there are actually 4 rules, because each dash expands into 2 possible rules, because yes or no. Okay. If there are 2 dashes in the same column, it will expand into 4 rules. Okay. So, in this case the expanded table is called an elementary rule decision table. An elementary rule is defined as one where every condition entry has got a assigned value, namely yes or no, in this case Boolean value, yes or no. So, the elementary rule decision table is one which is very nice to use, or is to kind of determine a number of things which we have been talking about, namely the missing rules, rules which are redundant, and rules which are contradictory, and so on. All these things are come out once you expand a table with dashes into a set of into an equivalent elementary rule decision table. That is, you can say that the first table and the second table are equivalent, in the sense that I have not done anything except put yes no for dashes. So, I have not changed anything else. It is a purely syntactic conversion, you might say. Okay. So, there is this conversion is somewhat automated, you might even say. Okay. A decision table with one condition should have 2 elementary rules, obviously, because yes or no. If there is a decision table with 2 conditions, there should be 2 to 2 or 4 elementary rules. Okay, like we had in the previous in this one, there are 4 elementary rules because there are 2 conditions. There are 3 conditions, of course 2 cubed, or there should be 8 possible elementary rules. In general, if there are k conditions, it will be 2 to the k. Each elementary rule must be distinct. okay, because it is the rule has got yes no, and you know, in other words the rules are all have got to be distinct, and each elementary rule must have a distinct action. Okay. Like in this case, each elementary rule, see now you can say they are all distinct, but you see you can see R11 and R22 are really not distinct. In other words, the same answers are there and the actions are different. So, that there is some problem with this table, that is what it means. Okay. If a decision table with k conditions does not have 2 to the k rules specified, it is supposed to be incomplete, because 2 to the, as I said, 3 rules, 3 conditions expand to 8, 2 to k conditions expand to 2 to the k. For example, DT2 does not have elementary rule. In other words, if I go back to this table, the all the 2 to the k, that means 2 to the k will have S, no, yes, no. Now, no is missing. So, that means this table has a missing elementary rule. So, it is called incomplete. Okay. If a decision table has the same elementary rule occurring more than once, like in the table which I showed, it is said to have multiplicity of specifications, because there are two SS answers in this case. There are 2 rules which are identical, and the multiplicity of the rules are there, and the C1 equal to S, C2 is Y occurs twice, that has got multiplicity of specifications. If actions specified for multiple identical rules are different, then it is called ambiguous specification. The specification is ambiguous. DT2 is an ambiguity, that say because if I look at this, as I pointed out, rule number 1.1 has got an action A1 and rule number 2.2 has got an action A2. These two actions are different actions. So, that means it has got an ambiguity. Because the R1 and R2 are identical, but are different actions. Ambiguity may be apparent or real. Let me explain what is meant by apparent or real. An ambiguity is said to be apparent if the rules leading to the ambiguity is logically impossible. In other words, if that particular rule is logically impossible, then the ambiguity cannot arise in practice. For example, S as answer, is it possible or not? Now, x greater than 60 and x less than 40 cannot occur simultaneously, because I cannot find a number which is above 60 and the same time below 40. Okay. So, that means this S as answer is not going to arise at all in practice. So, rule 1.1 and rule 2.2, so there is an actual, in this case then these two rules, there is the ambiguity in the table is not a real ambiguity, but an apparent ambiguity. Okay. So, apparently ambiguous rules is not an error, because the fact that it cannot occur. So, the question of an error does not arise. If an apparently ambiguous specification is real, that means if it can actually occur, then there is a contradiction. Like for instance, if x greater than 60 is S and x greater than 40 is S, then x equal to 70 will satisfy these inequalities. So, it means yes answer to the first one, and in this case C2 I said as yeah, you can say that the is less than 40 greater than 60, okay, but I am looking at the other case. So, if If 2 to the k elementary rules are not present, then it is incomplete. DT2 is incomplete because there is no, there is no specification of no. It is a missing one. Okay. Like in this case, you can, if you count the ones and see, you find that the no is now absent, because SS is there, yes no is there, no S is there, SS is there. If no is absent, and so it really means that that for that, if that particular rule arises, if that is x less than or equal to 60 and x greater than or equal to 40, that case there is no rule specified. Okay. It is incomplete because this is missing, and the question we have to ask next is, if it is really missing, is it a real kind of missing situation or an apparent miss? In other words, if it can't arise in practice, the fact that it is missing is irrelevant. But in practice, if that particular set of conditions are satisfiable, then obviously the no action is specified. So that means incomplete. I have not given an appropriate action for it. Okay. So C1 equal to n and C2 equal to n is logically possible because x less than or equal to 60 and x greater than or equal to 40 is possible. There is a value x equal to 50, which will make C1 equal to n and C2 equal to n. Okay. So 50 is less than or equal to 60 and also greater than or equal to 40. So thus DT2 has a real incomplete specification. So even though this particular decision tables looks very innocuous, very simple, it has a hidden incompleteness. Okay. And the incompleteness is found out, and also we find out the incompleteness can actually occur. So any test data which you give, if you give 50 as test data for that table and try to test it with 50, it will come back and say no action can be taken. That means there is no rule specified for that, and actually occurred because there is a data value which does satisfy this. Okay. A decision table which has no real ambiguities or no real incompleteness is said to be logically correct. That is, it has got does not have any incompleteness, and it does not have any ambiguity. Okay. There is, and both of them are real. That is, there exists data which will satisfy the conditions which will which if the data exists to satisfy the conditions and the rule is either missing or it is duplicated with different actions, then it is an error. Otherwise, there is no error. In other words, there does not exist any data, okay, which the point is, if the data exists which will actually satisfy the inequalities and you get to a contradiction, then of course it is an error. If data does not exist, it is not an error. Okay. And so a decision table which has no real ambiguities, that means has and has got no real no real incompleteness, then it is logically correct. Otherwise, decision table with logical error should be corrected. Otherwise, it is got incorrectness. Okay. A table with logical error should be corrected, obviously. Okay. In fact, one easy way of finding out the missing rules as well as ambiguous specifications purely syntactically is by mapping the conditions onto a map known as a Karnaugh map. You actually would have come across Karnaugh maps in your course on logic design of computers. In fact, the first course on logical organization or the first course in digital design, which covers Boolean algebra and also talks about the truth tables and converting truth tables to equivalent switching circuits and so on, also uses the same idea of a Karnaugh map. Karnaugh map is one which essentially is a two-dimensional structure, which also is an equivalent of the, in this case, decision table. In fact, you can look at the decision table as somewhat analogous to a truth table. Okay, a truth table with multiple outputs. Normally, in a truth table, you have a set of independent variables and one dependent variable. Okay, there are some truth tables where you can have multiple independent variables and a set of dependent variables. But in a truth table, the dependent variables are independent of one another. In other words, within themselves the dependent variables are independent, and so the also question of sequencing does not arise in that case. It is purely a syntactic equivalent, whereas in this case there is semantic is involved. So DT is not the same as truth table for a simple reason that actions are actions which are carried out and they have certain sequence to be carried out. So it is not like a multiple output, multiple input truth table. Okay, so they're even though they look similar, they are somewhat logically they have different purposes and they are used in two different fields. For one in the field of logic design to design switching circuits, and in the field of systems analysis and design to be able to analyze word statements and to kind of program those word statements, and also used as a communication aid between the user and the program developer. So, but the point is, many of the tools and techniques which you have learned in logic design become again useful in looking at decision tables or examining decision tables. So, to some extent it is not something very new to you, it is something which you to some extent already know. So, I will go a little bit faster in terms of saying about Karnaugh maps and how to expand Karnaugh maps and so on. And a Karnaugh map is named after a person who called Karnaugh, who first developed it or invented it, you might say, and it is in fact abbreviated as K map. It is a two-dimensional diagram, and it also lists all the conditions and all the actions. In the case of Boolean truth table, the ones and zeros are used for C1, C2, and normally one table is written out for each independent variable, whereas in this case I am using the same table, same Karnaugh map, to be able to also show the different actions to be taken, so that it becomes in other words, I am mapping the table onto a Karnaugh map which reflects whatever information is contained in the table, and dt is now contained in the Karnaugh map. So, the Karnaugh map has got two conditions C1, C2. So, there are no S along the top row, and values of C2 are no S along the column. Okay. So, if you take no, as we found out, for no action is specified. So, you put a question mark. For yes no, C1 yes, C2 no, there is action A1 which is specified. Okay. If I go back, I can actually see this. Okay. So, I am actually what I am doing is to map this. So, A1 if it is C1 is yes and C2 is no, then A1. Okay. If C2 is yes, C1 is yes, C2 is yes, it is A1, and that is exactly what I am taking this same table and putting it in the map form. Okay. So, I essentially put that table into this map, and I said, once you cover it, put these things, you can immediately see that SS has got a problem, because there are two actions specified. If more than one action is in one square, it is an ambiguous rule, okay, because there are two actions are specified for that. If a square is empty, it signifies an incomplete specification. So, the advantage of a map is you can, once you map the table into the map, it more or less becomes obvious what is missing and what is ambiguous. Now, let me take another example of taking the point. The reason why I am putting this example is that if you specify a certain thing as in structured English, it looks all right, but when you map it onto a distinct table and also to a Carnot map which is equivalent to that, you find out that it may be incomplete. Like for instance, structured English procedure is given. If steel is checked, and the whole idea is there is a set of rules given by a metallurgical engineer about classifying steel, okay, and the rules which are given is that if the carbon content of the steel is less than 0.7, and if the Rockwell hardness, there is something called Rockwell hardness which they measure for steel, if it is greater than 50, and if the tensile strength of this particular steel is greater than 30,000. See, the carbon content, Rockwell hardness and tensile strength are properties of the steel which is being manufactured. So, you check these three, that is, if carbon content is less than 0.7 and Rockwell hardness is greater than 50, and if the strength is if the tensile strength is greater than 3000, then steel is of grade 10. If it is not, tensile strength is not of strength 30,000, it is grade 9. If then the nested if says that if the Rockwell hardness is greater than 50, but if the carbon content is less than 0.7, if the hardness is not greater than 50, then steel is grade 8. If none of them, see, carbon hardness is less than 0.7 and none of these conditions satisfied, if the steel is graded 7. So, this is essentially what the structured English statement says. If I put it into a form of a table, I have got three conditions: carbon content less than 0.7, Rockwell hardness greater than 50, and tensile strength greater than 30,000. You see that first of all, see, interpreting a nested if then else statement which is given as a structured English is not straightforward. In fact, when I try to do it, I found that I got to properly bracket and tell you, okay, and I could have easily made a mistake in incorrect bracketing. That fortunately will not arise in the case of a table, because I am more or less combinatorially looking at all possibilities, okay. And if there are three conditions and each condition can yes or no answer, there are possibility of total of 8 possible rules, 2 cubed rules. So, the first rule says if all three are satisfied, all three conditions satisfied, then the grade is 10. If the first two are satisfied and third is not satisfied, then grade is 9. If the first is satisfied and the other two are not satisfied, grade is 8. If none of them is satisfied, grade is 7. That is what the rule says. Now, what if the first one is satisfied and the last one is satisfied? That is, carbon content is less than 0.7 and tensile strength is also greater than 30,000, but Rockwell hardness is not greater than 50. What do I do? Do I classify it as 7 or do I classify it as 9 or 8 or what, or is there a new classification of 6 I have to put? So, in other words, all the other cases are not specified in this particular business rules converted into a structured English statement. So, structured English statement sometimes can be misleading. It may look complete, but it may not be complete in the sense that all possible contingencies may not be entirely covered, which we find in this case. There are 4 possible rules for which it is not covered. Okay. It may happen, and I have no idea because I am not a metallurgical engineer, that if carbon content is greater than 0.7 and tensile strength is greater than 30,000, if the hardness is less than 50, may not occur at all, or even if it occurs, it is rejected. So, if it is rejected, then I must have one more rule saying that the carbon is the particular thing is not accepted, or if I assume that grade 7 is non-acceptable grade, then of course I can say that I can put 7 for all of the rest of the things. Okay. So, the point is that the missing rules, it is not for the analyst to decide what to put in that missing rules. It is for the user, in this case a metallurgist who has given these rules, to tell me whether these will be relevant or irrelevant. See, for steel it may not be correct at all, these points may be irrelevant. The question I may be asking is stupid, okay, but I do not know whether it is a stupid question or not, or whether he has missed it or not. Okay. So, it is important to be able to point out the fact that when I look at your rules, for these rules there is no action specified, no classification to be given. So, what do? Do I leave it unclassified, or does not ever occur in practice, or do I give a new classification number and so on. So, the point is that the decision maker is not you. Decision maker about the action, namely giving grade, is the user. So, you have to get back to the user. So, if you map it into a Karnaugh map, it is quite obvious. There are 3 conditions are independent, and then there are question marks. So, decision ability is incomplete, and incompleteness is also maybe it looks like it is a real incompleteness, okay, because in the absence of any information, it is a real incompleteness. I am taking one more example of trying to analyze a given decision table to find out whether it is got any errors in it. A set of this decision table is given for management as arrears in a particular company. The arrears management table, which is given as payment in current month, that is, there are four conditions to be checked for arrears management. If the payment it may be that of a credit card company. You see, the credit card company gives you cards, and at the end of the month you are supposed to pay, and if you do not pay, of course they charge you interest, and if you do not continuously pay for a certain number of months, they may cancel the card, okay, and if you do not pay for 1 month, they may send you some reminder. So, these are all different actions which the company may take, and they are called business rules taken by the company. So, in this case, the payment in the current month is greater than a minimum specified payment. Normally, in a credit card company, you are supposed to pay each month, even though you have run up a debt or something like you may have purchased items up to 5,000 rupees, but they will tell in the statement that it is enough if you pay 200 rupees. The rest of it will be charged in terms of the interest will be charged on that. Okay. So, there is certain kind of minimum specified payment. So, payment in the current month is greater than the minimum specified payment, the answer is yes. Send letter A, that is you send an acknowledgement letter, thank you for your payment, but you still have an arrears of so and so, and that arrears will carry an interest of so and so. Okay. If it is these letters normally generated automatically by computer and sent out to the customer, okay, because this is essentially a set of rules implemented and by actually a computer program. Okay. The rules have been given by a manager, but ultimately the actions are automated. That is the whole idea of using computers. Okay. So, the first rule says the payment in the current month is greater than minimum specified payment, you send letter A. Okay. If the current month it is not greater than minimum specified payment, that means he has given less than what was specified as the minimum payment due. That is, as I said, every credit card company has some minimum payment which they allow. If it is below minimum, payment card is greater than or equal to minimum, so it is below minimum, and payment in the current month is greater than 0. That means he has given some money, but he has not, his given money is, suppose 500 rupees is to be paid as what is required of him, and he has paid partial 200 rupees, but not 500 rupees, then payment in the current month is greater than 0, but it is not the full amount. Okay. And the actual arrears is greater than 3 times minimum specified payment per month. That is, if the arrears, there is a minimum specified payment for each month. If you take the 3 months average, and if it is greater than 3 months specified payment per month, then you send letter B, giving him some kind of a warning, maybe saying that your arrears is building up, and so interest payments will start accumulating. If the third rule says that if the payment in current month is greater than 0, so also, but it is less than the what is required in the month, and actual arrears is less than 3 months minimum specified, then you send another letter C. Okay. So, this is a third possible rule. Okay. So, it may the actual letter is for the manager to decide what letter will be sent out by the machine. And rule 4 says that first whether the first two are irrelevant, if no payment has been received, any payment in the last 3 months, no. Okay, that means no payment has been received in the last 3 months, and actual arrears is exceeded 3 months minimum specified arrears per month. Okay. So, in fact, he is accumulating debt very fast, and then you say send letter D. In the case of rule 5, payment in current month is greater than 60, no, that is greater than 0, no, that means it is less, no payment has been received, and any payment in the last 3 months, yes, some payment has been received in the last 3 months, and actual arrears is greater than 3 months, less than 3 months, then you send letter E. Okay. The last rule says that any payment in the current month is not greater than 0. That means it is less than or equal to 0. That obviously means 0, no payment. Okay. And any payment in the last 3 months, yes, there is some payment, and actual arrears is greater than the 3 months arrears, then you also send letter D. There are two cases, rule 4 and rule 6, you send letter D, and the other rules you send A, B, C, D, E. Okay. So, there is some arbitrary, I just picked out of my hat. Okay. Now, the next question is, how do I analyze this this set of this decision table to find out whether the rules which are given are complete, the rules which are given are are not only complete, but they don't have any the ambiguities, and if there are ambiguities, are they real ambiguities or are they apparent ambiguities? That means, are there any contradictions in the rules? Okay. These are the points we found out before accepting these rules and implementing on the machine, because you will find out later on, if you did not check it out, check out the DT carefully, you will find out later on that a particular case may arise when the wrong letter would be sent, okay, and then the customer will be extremely unhappy, okay, or the machine will just hang up and say for this particular set of conditions I do not know what to do. Okay. If it is an incomplete specification, that means the machine will hang up and say I do not know what to do. So, the first thing we do before we analyze is to kind of convert this into a that is, take each condition and use variables for that, because it is easier to work with variables, because mathematically we can analyze it easier if we use variables and inequalities. So, in this case I am using x for payment in the current month, x, and m is for the minimum minimum specified payment. So, I have converted the payment for the current month as x and the minimum as m. Okay. C2 is payment in current month, that is x x greater than 0 is the second condition. So, the second condition is x greater than 0. Third condition is independent, that is any payment in last 3 months. Last 3 months payment has nothing to do with the payment in the current month. Okay. So, there is a new variable y. Okay. So, I put y for C3. C3 is any payment in last 3 months is when y y is greater than 0, and actual pay arrears is greater than 3 months minimum specified per month. Okay. The actual payment is some actual arrears is some z, which is a variable, because the arrears will change from person to person to person, and it is not related to x and y. So, I put a new variable z, and it is greater than 3 months m was what was used for minimum specified payment. So, this is 3 times minimum specified payment per month. So, I converted the table, the condition stub into equivalent quantified inequalities based on the what I am saying, by inventing or putting variables instead of words. Instead of putting words, I have used mathematical variables which represent the words, and the reason I have done that is obvious. That is, I am effectively going to be able to analyze it mathematically only if I do this first. So, that is exactly what you have to really do. Given a table, you want to start looking at the checking the table for contradictions and so on. The first thing you have to do is to be able to invent simple variables and equivalent and inequalities, if are equalities or whatever, based on the specified condition, and use that for further analysis. The further analysis then becomes fairly straightforward. So, what I have done is taken this table and mapped it into a Karnaugh map. Okay. Now, in fact, the way in which to map it into a Karnaugh map is, as I pointed out, let us take an example. Rule 1. Rule 1 has got action A1. Okay. Rule 1 will expand into how many rules? Because there are 3 dashes in it, rule 1 will expand into total of 8 possible rules. Okay. So, rule 2 will expand into 2 possible rules. So, I will add 8 plus 2 10, third will expand into 2 plus 2 12, fourth will expand into 4 16, next will expand into 2 more 18, plus last one expand into 2 20. So, total of 20 rules, this table will expand into total of 20 elementary rules. So, if I convert this into an elementary rule decision table with only yes or no answers, there will be 20 elementary rules, whereas the total possible elementary rules with 4 conditions in a table are only 16. So, there are 4 excess rules, and so that means there is some problem with this table to begin with. So, there are some excess rules. So, I will be essentially certain rules may map on to multiple actions, and I do not know by just counting whether there is any missing rule or not. Okay. And that is what exactly the Kano map does. It when you map it, take each rule one by one. Let me just take the first rule and see which is action A1. First rule is yes for C1, okay. C1 is yes, and C2, C1, C2, C3 can be anything. Okay. Now, if I look at C1 is yes is last column, okay, and C2 is irrelevant. So, A1, 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 all 4 come along that. So, 4 are there. So, I have 4 more. Okay. Second column is also C1 equal to yes. C1 is yes, the second column. Now, again A1, 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 A1. So, the C1 equal to y will map on to 8 rules, which will be essentially the 8 squares in this map. Okay. The 8 squares in the map are the last 2 columns in the map. Okay. The last 2 columns in the map essentially I will have all A1. Okay. And if I similarly I go on. Okay. If I convert second one, is no y dash y. No y dash y will become no y is C1, C2 is no y, dash y becomes no y and sy. So, A2, action A2 maps on to the second row second column, and third row second column. Okay. I have put that A2 down. Similarly, if I take the next rule, namely that will be no s dash s. So, no s dash s will become no s is C1 C2 no s, and dash becomes either no s. So, the first row first column, first row second column, and in fact I had to go along second column and the last row, they are all action A3. So, I mapped on to action A3. Okay. And similarly, the R4 will map into 4 actions. Okay. 4 actions, in fact I can see that the no s, okay, no s for C3 C4. So, if I go along no s for C3 C4, no s is second row for C3 C4, and all A4 will map on to that particular row. Okay. So, I continue like this. In other words, I just expand the dashes into yes no and fill up this table. Once I fill up the table, I mark with stars those particular, in fact there are stars and pluses. I will come to why I put pluses and stars in the next lecture, but I put a question mark where is a missing rule, for nothing is specified, even though there are 20 rules. In fact, if you count the total here, 3 plus 4 7 plus 3 10 plus 3 13 15 17 30 rules are already there. Okay. So, that is where I will stop now and continue next time with the with analyzing this further.